Okay, so the value of K is what? Rate constant, right? And it's often used to find the relative rate of your reaction. For reactions with K greater than 10 to the 90th, the reaction is considered fast. For reactions with K equal or lower than 10 to the 90th, the reaction is considered slow. So we have here a table. This table shows 0, first, and second order. The rate law, if the order is 0, sorry, if the reaction here is ordered 0, the rate will be equal to K. And the concentration versus time. So if you needed to find the concentration, for example, of A in the specific time, you're going to be concentration of A equal minus KT plus to the initial concentration. This T is for time. The minus K, this K is the rate constant. In the half-life, so the half-life is the time that the sample gets to decompose in half. It's called half-life. So to find the half-life for a zero order reaction, you be initial concentration divided by the 2K. In the units, it is for the rate constant for zero order reaction, the units is molar per second. One, if this order is a zero order reaction, you have it here, right? And if it is a first order, the rate is equal to K times concentration of A. And to calculate the concentration of A, so or to calculate the time in a specific data of concentration and initial concentration, you're going to use this equation here. Okay. And the half-life for first reaction, it is 0.693 divided by K. The rate constant units for first order reaction, it is per second. Now, let's go to the second order. For second order, the rate is equal to K, A to the second, this here, right, to the second. And the concentration versus time, the equation to use it, the integrated equation related concentration time, it is 1 over initial concentration of A equal to K times T plus 1 over the initial concentration. And the half-life is 1 over K divided by initial concentration of A. In the units, the K units, it is per molar per second. Molar to the minus 1, second to the minus 1. So you can see here, if the order changes, the K units change. Are you seeing here? It's for 0, first, and second. So let's try to understand it here a little bit more. If the reaction is zero order, so let's say if you double the concentration of A, what happens with the rate? let's understand here. How is the equation here? Rate is equal to K. If it's zero order, that it means A to the power of 0, right? And what does mean anything to the power of 0 is equal to what? Is equal to 1, right? But it means if you double the concentration of A, we will not change anything here. So for 0 order, if you double the concentration of A, we will not affect the rate. Okay, now let's go to the first order here. If you have, like for first order, you have the equation like R equal to rate constant times concentration of A to the first. So the order, remember, is what is to the power here, right? Here is 0, here is 1. So if you double the concentration of A, so let's see. If you double the concentration of A to A, what's happen with the rate here? If you double the concentration of A for the first order, we will double the rate. So for first order reaction, if you double the concentration of A, that means if you double the reactant concentration, you double the rate. Now let's go to the second order. If you have second order, what's the equation for second order? Like R is equal to K, A to the second, right? Because it's power of 2, that means second order. So if you double the concentration of A, let's say 2A, what happen here with R? Will quadruple, right? Rate will quadruple. So for zero order, does not matter what to do for the concentration of A. If it's A to the zero order, will not affect the rate. If it is first order, it will be the same proportion. So if you double the concentration of A, will double the rate. If the concentration of A will be, you increase in 3 times the concentration of A, that means your rate will increase 3 times. But for order, the second order is going to be to the power of 2. The second, that means everything that you do here with the concentration of A, need to consider they're going to have a power of 2 here. So if it is 2, 2 to the second, it is 4. So we'll quadruple, right? If it was 3, if you concentration of A, you change it to 3 times higher, going to be 3 to the second. That's going to be what? It will be 9. That means the rate will change it to 90 times, to increase 90 times. Okay. Okay. So practice problem number 4. Finding the rate law from initial rate data. The initial rate of reaction A plus B going to C was measured for 3 different starting concentration of, it's blurry, a little bit blurry. Let's wait here. It's better, I think, of A and B. And the results are as follows. So here, concentration for the first experiment, the second experiment, and to the third experiment, right? So let's figure out here. Now, letter A, to find the rate law for the equation. So what's the rate law? So initial gonna be like R equal to K, concentration of A, because we have reactant A times reactant B, right? But you don't know yet the order. So let's do in here. Let's solve it to find the order of this reaction, to find X and to find Y. So how are we going to find the X and Y? So let's first look for X. X is the order of A. So to find the order of A, we're going to look to this table here and figure out which experiment is changed for A and is constant for B. What experiments we'll have here that the A is changing and the B is constant? One and 3, right? 1 and 3. 1 and 3 double concentration of A's. Increasing is change, right? But B is constant. It means you can investigate what's the order for A. If you look in experiment 1 and 3. So let's do it here. Rate 3 divided by rate 1 is equal to concentration of A for the trial number 3, right? Divided by concentration of A for the trial number 1 to the power of X. Because what we want to find, we need to find X. So let's plug here. 3, it is 16.0 times 10 to the minus 3 divided by 1. 1, it is 4 times 10 to the minus 5. The unit here is molar per second, right? And concentration of A3, so A on the trial 3, it is 0.2 divided by concentration of A in trial 1, 0.1. I'll just put the unit here. Anyway, the unit is going to be canceled out, this with this, just for you to get use it to all of the units, hours, right? Power of X. So let's do the calculation here. 16 divided, so this divided by this. Sorry, this is 16 to the power of minus 5, right? Minus 5 here. Gonna be what? 4 equal to 0.200 divided by 0.100. It is 2 to the what? To the X. Which number we're gonna make it X here? So 2 to the second, right? 4 to the second and 2 to the X. So that it means X is equal to 2. Okay, good. That it means the A is the second order, right? Let's do the same thing that we did to find Y, to find the order of B, the B order. So let's do here. Let's look your data. What is changing here in B? What experiments is changing for B, but not changing for A? A concentrations are constant here. Experiment 1 and 2 is changing for B, is not changing for A, right? So yes. So let's go ahead here. Rate 2 divided by rate 1 is equal to concentration of A to the second divided by to the A first to the Y here. Then what's the rate second, the second here? 4 times 10 to the minus 5. So the second rate, right? And for the first one, the same thing. Okay, and then let's go ahead and look for the concentration of A. Sorry, I messed up here, right, guys? What was it? Should be B2. I'm sorry, B2 and B1. Why? Because here A is changing. So A, 1 and 2, A is constant and B is changing, right? So to investigate the rate order of B, we're gonna choose the experiment 1 and 2 that B is changing. So which one B is changing? 2 and 1. So let's go ahead here. 0.200, 0.100, the power of Y. So this divided by this is going to be equal to 1. And then divided by this is going to be equal to 2 to the power of Y. So which number will be, so 2 to the power of which number will be equal to 1? So any number to the power of 0 will be equal to 1, right? That means here Y will be equal to 0. So that means Y is equal to 0. And that makes sense, right? Here, the concentration of B changed, but did not affect the rate. So that means the order for B is 0. Now let's go ahead. We find the rate law here. Rate law is equal to K to the power of A. X is what? Is 2. And B, what's B? B is to the Y. Which one is Y? Is 0. And what is B to the power of 0? Anything to the power of 0 is what? B equal to 1, right? That means the rate law can just be written as R equal to K to the power of 2. Okay, there's the answer for letter A. Now the B is to find the rate constant. So to find the rate constant, you can choose either in experiment here, 1, 2, or 3, plug the data here to find the experiment, to find the rate constant. So let's go ahead here. B is equal to, let's choose experiment 1. Experiment 1, the rate, so remember the rate equation, the rate law for the reaction for the is R equal to K to the power of A to the second. So that it means rate is equal to 4 times 10 to the minus 5th here molar per second is equal to K and to the power to A. Which one is A? A here is 0.100 for experiment 1, right? 0.100 molar to the second, okay? So let's go ahead and do rearrange here. We're gonna be K is equal to 4.0 times 10 to the minus 50 here, molars per second, 0.100 to the square, right? Don't forget about this, to the square. And m to the square, right? It won't be yeah. So let's just, so I'll go just do this way just so you can see how we're going to be canceling here. So because m to the power, m to the second is m times m, right? So we're going to be doing this division here. You should find it 4.0 times 10 to the minus 3 minus to the right, and you cancel here molar with molar. So the unit here going to be molar to the minus 1 and second to the minus 1. So this is the result for K. The answer for K, the rate constant, it is 4.0 times 10 to the minus 3 per molar per second. And look at the unit for K. So this reaction here is a second order, right? Here, second order. So look at what we have here. The K unit, the K unit is for K. For second order, it is per molar to the minus 1, second to the minus 1. Now, the letter C is asking the rate of the reaction when A is equal to 0.050 and B is equal to 0.100. So we're gonna use the same rate law. This is what we found. We're gonna keep the same for all next ones here. The rate is what we're gonna calculate it here. The K is your rate constant. So the rate constant will be the same for any experiment here. So any A to the second, it is 0.050 So times 0.050 to the second. And then you can calculate your R. So when you do this, your R is gonna be 1.0 times 10 to the minus 5th here, molar per second. Okay. So just shown here, summary what we're talking about. First order reaction, the law becomes R is equal to K to the A. So some rates depend only on reacting to the first power. These are first order reactions. There's the law here. And then here we have the deduction here going from rate is equal K to the concentration of A to find the rate of the reactant, right? Here we're gonna use it minus change of A divided by the change in time, minus because it's it's a reactant. So that means you can equalize this portion with this portion because both are equal to the rate. So you can equalize for here. And then when rearrange here, delta T, so delta A divided by A equal to the minus KT. So we're gonna integrate here to find it, to gonna add the not natural logarithm here. So we can rearrange it, gonna be this one. That means if to find the concentration of A in a specific time, we're gonna be using natural logarithm of A is equal to the minus K, T is for time, plus natural logarithm of A. This one here is the initial concentration of A. In this, A is for the concentration of any time in the reaction. And this follows the equation of a line y is equal to mx plus v here. And if you do the plot here, natural logarithm of A versus time, you have is a linear. Okay, so here, evident that the conservation of methyl isonitrile is to acetonitrile, have the equation here. It's first order, the plot of natural logarithm versus time is linear. So look here, if you plug it, the time versus concentration here, I would think that it's not linear here. It's not linear for this one. Why? Because if you plug directly time versus concentration, if it is linear, would it be 0? But because it's not, this one is not a linear, so that means it's not 0 order. Now let's look to the second graph. The second graph is what? It's time for x, and your y is the concentration of natural logarithm, right? So that means what we have here. The results in a linear. If it is linear, então, in that case, because it just became linear after you did the natural logarithm, then it is, so it would be, it's a first order. Now let's go to chat to continue. Let's continue here. Okay, now I see, so problem 6, practice problem 6, the decomposition of a certain insecticide in water at 12 degrees Celsius follows first order. Kinetics with a rate constant of 1.45 rate per year, and a quantity of this insecticide is washed into a lake on June 1st. So lead to a concentration of 5.0 times 10 to the minus 7 grams per cubic centimeters. Assume that the temperature of the lake is constant, so that there are no effects on temperature variation on the rate. A. What's the concentration of the insecticide on June of the following year? So let's use this. The first order, look here, is giving to us information. That's first order. If it's first order, we're gonna using this equation. Natural logarithm of A is equal to minus KT plus natural logarithm of initial concentration of A. So we don't know the concentration at the time yet, the insecticide concentration. So we're gonna work to find it. Minus K. K was given here, the rate constant, times T. T was the time it was in year because it was asking what will be the concentration in the following year. So the time is going to be 1 year after, right? This is your time. This is your K. And this is your initial concentration. So after you plug it everything here, this portion here should get minus 15.96. Right? So, and then you need to plug, okay, what's the natural logarithm of this, the insecticide here, right? Insecticide. So we need to apply the reverse. What's the reverse of natural logarithm here? We need to rearrange here. We're gonna be insecticide concentration will be equal to what? So E minus 15 to the minus 1596. That should be equal to this number here, right? Okay. So, and the B is asking how long will it take for the insecticide concentration to decrease to 3.0 times 10 to the minus 7 grams per cubic centimeter. So we're gonna using initially your concentration here, you have the concentration in the specific time. So the question is how long will it take for the insecticide concentration to decrease? So we're gonna take it. You have the A in specific time here minus K. T is your unknown plus natural logarithm of the initial concentration of here. You have it This one's your time t. So if you rearrange it here, your time should be 0.35 years. So Praxis problem 6. I know, right? I did a 2 Praxis problem here. So let's say this is Praxis problem 6. The second one. Yes, so let's see what I did. Yeah. So I have a 2 Praxis problem 6. The second one that will gonna be a Shockley points. So what we're gonna do here? So remember that we talk about the graphs, right? So we're gonna plot time for X in seconds and the concentration for Y. So we're gonna plot 3 different graphs. So the first graph gonna be for this one here. So if when you plot this, if you find linear, if it is linear, so and then the answer gonna be will be 0 order. Right? And say, let's say that you started here, said, okay, it's not showing linear. So that means it's not a 0 order. So let's go to the second graph. The second graph is going to be timing for your X, and your Y would be natural logarithm of the concentration of NO2. So if this portion here, if linear, like then it will be first order. And let's say that you did everything. He still did not find it. So let's go ahead and do this. The third graph going to be time over. So time versus 1 over the nitrite concentration. So if this graph here, if linear, if linearly, then it will be the second order. So gonna make it the 3 graphs, right? And I'm gonna then upload them in just one file and upload on Canvas. Okay, this was the lecture today. So tomorrow we're gonna talk about the half-life. Half-life is the amount of time it takes for 1/2 of a reaction to be used up in a chemical reaction for first order reaction. So we're gonna be working this tomorrow. Okay.